Security enhancing CAN transceiver is a topic for today, and I will immediately jump into the topic. If you want to make a car secure, if you want to have certain IT cyber security, then you definitely need more than one measure in your car. And we as NXP, we propose at least 4 or 4+1 layers. One layer would be, as you can see here, the secure interfaces. So if you have, let's say, an antenna where you are connected to the Internet of Things, then of course you need to secure this antenna where all the data comes in. And likely you will do this with a secure element. The next level then is a secure gateway. So if somebody is able to circumvent the first barrier, so bring whatever malicious software or data in your car, then of course you want to have a secure interface so that this malicious software or data cannot spread out over the entire car. Next level would be then the secure network, secure onboard communication, and this is where I would like to go a little bit more in depth to see what we can do on the CAN physical layer. Last but not least, you need the secure brains, the secure microcontrollers, likely featuring secure boot, for example, in order to prevent a hacker to succeed with this attack at a module which, for example, controls actuator. And if we talk about 4+1 layer, then the 5th layer in that sense is the secure car access, where we are talking about keys for remote keyless entry, remote keyless go. And you have recently seen that, for example, some applications for your smartphone that would allow to open the doors are not secure. Just released last week a big report about weaknesses there. Okay, let's focus on the CAN physical layer. What can the CAN transceiver do in order to improve the security, the cyber security in a vehicle? Normally in a vehicle, you have node E, node A wants to send data to a node B. And of course, there are a couple of different nodes. We have up to 100 nodes sometimes in some vehicles, but I want to focus only on 3 nodes, A, E, and B. And I assume that node number E has a couple of interfaces. For the convenience of the driver, we see Wi-Fi interfaces, you have near-field communication, Bluetooth, USB, whatever to connect your entertainment devices, for example, to the car. This is nice not only for the driver's convenience, but also for the hacker. This is nice because this has a very broad attack surface. Also, the hacker can hook up his devices to those interfaces and try to bring his malicious software into the system. So if now the hacker was able to bring compromised software on the node E, so the node E is under control of the hacker, likely it can be controlled even remotely because there is a connection via the internet, via 4G, whatever technology to the outside world. And then node E can start send CAN messages with the same identifier as node A would send on the bus. Nice. This is a spoofing attack because now the node E pretends to be node A. We can imagine this is, for example, a CD or radio set where via the radio connection the malicious software came in. We see node A, maybe the engine controller, and we can imagine node B is the throttle. And this is now a very nice situation for the hacker because he can now move the gas pedal by sending CAN messages from the radio set, which normally would come from the engine controller. And of course, node B now needs to decide which of the 2 messages is received as the right one. But node B is definitely in a dilemma. It cannot decide. It does not know which message is the correct message and which is not. And now the transceiver comes into play because we can say, okay, solution 1, the transceiver in node E is only allowed to send a certain set of CAN identifiers. So we would program a wide list of CAN identifiers that are allowed to send. And if node E tries to send a message with, for example, CAN identifier 1, 2, 3, then the transceiver sees, okay, this identifier is not on the whitelist, and this message is blocked by the transceiver. What is the implication? The message occurs on the bus, yes, it's there, but in the end of frame field, I still have the chance to invalidate this message by sending an error flag, an active error flag. So all receivers will discard the message, and then I can exclude node E from communication. Maybe until next power on, or maybe for a minute or whatever. Benefit is I have only one error frame on the bus, and why this is a benefit you will see in the next slide. There are other implications, or there are other things that I can do. If, for example, node E can block a certain identifier, it can also block identifiers which are allowed to be sent, but it can block them if they are sent too often. So if, for example, node E is allowed to send a high priority message, and this is configured in the whitelist, so he is allowed to send it, but now he does not send it every 100 milliseconds, but it starts to send it even every millisecond, for example, to flood the bus, then he would block out all the messages with lower priority, for example, because they would lose arbitration. But also in this case, the transceiver can step in and say, okay, for example, this node is only allowed to generate a bus load for whatever, 10%, for example, and if the node is sending more than 10% of bus load, then the transceiver shuts down. This, of course, does not help if node E does not have this transceiver. So if E is, let's say, a module which is an aftermarket device and has been connected later, so it's not under control of the OEM. And then I can do something different if I want to protect that. Then, for example, if node E is sending the identifier which it should not send, then the node A can also say, okay, this identifier belongs to me, and now if somebody else is sending this, then I'm invalidating the message with an active error flag. So spoofing protection can also be done on the receiver side. Now the implication is, of course, that if node A sends the active error flag and the message is invalidated, then the node E would repeat the message. So it will do this 16 times, and it gets 16 times the error flag. Then it goes error passive, and it repeats another 16 times. It gets another 16 error flags, and then it went bus off. So now you know why the possibility to stop the transmission in node E has a benefit, because there's only one message and one error flag on the bus. This helps also to protect in case node E is not under control of the OEM. So if an aftermarket device is connected maybe to the ODB port, then still node A can protect the messages it would send and cannot be spoofed. I can also do a little bit more. For example, if node E is not a real CAN IP, but just a whatever software implementation that does some bit banging on GPIO pins, then maybe node E may wait that node A sends a certain message, and then it steps in after node A has won arbitration, for example, and then starts tampering the message data, the content. And if node A is error active, then it's in the first place not a problem, because then node A says, okay, I see a bit error and throw an active error frame, but after 16 times node A would be error passive. And then node E can tamper the data, because node A would then stop transmission, not send an error flag, and node E can make the message complete with the data content he likes to have, and he can also send a correct CRC, so every other node will receive and acknowledge. This does not work, of course, if node A is not present. For example, if node A is unpowered, or, for example, node E pretends to be an offboard test tool, which typically is connected while the car is in the garage. If the module is disconnected, you're going back on the road, then E can definitely pretend to be an offboard tester. So then we would need solution number one to protect that case. Of course, the hacker can also always restart node number E. You cannot prevent him from restarting his attack. And of course, you always have this 32 error frames on the bus and a certain peak bus load in case the attack takes place. So we have, in the receive path, we have the feature spoofing protection and tamper protection, and in the transmit path, we can do transmission whitelisting, so only sending allowed identifiers, and we can do flooding protection. In the receive path, we have, let's say, intrusion detection, while in the transmit path, we do intrusion prevention. This is nice to do it in the transceiver, because now I have independent operation from the host. The software and the microcontroller may be compromised, while the configuration of the transceiver is fixed, and the compromised software cannot harm the bus. For sure, I need configuration, except for the tamper protection. As a tamper protection, the transceiver just needs to detect that a transmission was started on TXD, and the message was aborted on TXD, but still a correct message was received from the bus. Then I know a different node has taken over the message, so this was tampering. I can issue the error flag. This does not need configuration, while flooding prevention, for example, needs a configuration. A certain node may be allowed to send or contribute 6% to the bus load. Another node may be allowed to contribute maybe 15% to the bus load. So I likely need to be able to configure that. Spoofing protection also needs configuration. I need a list of identifiers to which I put an error frame on the bus. And also the transmission whitelisting needs identifiers so that the transceiver knows which identifiers are allowed to be sent on the bus. Nice thing is that the configuration for the spoofing protection and the transmission whitelisting can be the same, because if one node is allowed to send a certain identifier, all the other nodes are not allowed to send it. So it's simple. There might be some rare exceptions that also likely can be handled by the configuration, but basically the identifiers in both lists for spoofing and transmission whitelisting are the same. How do I do the configuration? Our idea is that configuration is done at the tier 1, so the module maker at the end of module production will configure the identifier, so it will program the device. Then he can test it. And when he has seen that the test fails, then he can reprogram, and if the test succeeds, then he will lock the device, like, let's say, burning a fuse on the device, and then it can never be reprogrammed again. So also a hacker does not have a possibility to update the configuration or to attack the device as such. So how do we build such a transceiver? How can we make it? It's rather straightforward, and we are almost there. So we are using a transceiver, and we have a couple of transceiver IPs available in our company, and also other semiconductor makers have that. We put a CAN decoder in it. This is also something we have some experience with. We have partial networking since a couple of years. Next step is that we enhance a CAN decoder to a CAN FD decoder. Also, this is something we did in the past as NXP already. We have the CAN FD shield, and we have shown this, for example, at the last CIA Plug Fest. So the CAN FD decoder in the shield works perfectly. And finally, we now need simply to add a set of policies that we store in our memory. So the CAN decoder delivers all the data, what's happening on the bus, what's happening on the TXD, and I just need to add the policies to decide whether I send an error flag, for example, or whether I block the TXD path. This is, let's say, what we have available. Question, of course, what comes next or what might come next. And next step might be that we replace our fixed state machine by a programmable core. Then, of course, we could also make use of cryptography. We could add a secure storage and have a key or a certificate stored there. But this is a little bit in the future. Here we are doing some, let's say, testing and experiments. Let me conclude then here. We have a feature summary, so we have 4 nice features to make the life of the hacker a little bit harder and let him have less success in the vehicle. We can do the spoofing protection by sending active error flags on reception of messages that I do not want to see on the bus, sent by others. I have the transmission whitelisting, where I can say, okay, only a certain set of identifiers are allowed to be sent. I can prevent the message takeover. So if I start, let's say, to say a sentence and somebody interrupts me and completes the sentence, or in this case the frame, then I also can throw an error frame here and pretend this. And last but not least, I can do the flooding prevention. So if a node tries to send more or contribute more to the bus load than he is allowed, then I can also stop that. The advantage here is I can do it really in a standard transceiver package, so I have a drop-in replacement for all the transceivers which are on the market. So whether it's, for example, SO8 or SO14 package, I can, let's say, offer a solution, the same package, pin compatible to what's there out in the field. So I just can replace the transceiver in my module and don't have any other hardware change. I also have, with that, I have a quick fix available for vulnerable modules which are already out in the field. Because by just replacing the transceiver, I get already the enhancement of my cybersecurity. I do not need to touch the software. And if you think about modules which are maybe 5 or 10 years old, then the micro might not even have any capabilities to do cryptography or other fancy security things. So you just replace the transceiver, don't touch the software, and everything is fine so far. No, cryptography means also I do not need to take care about key management, because as soon as you start with cryptography, the question is, from where do I get my key? How come the initial key on the module? How do I do key diversification? How do I do key update? And this is a very complex thing, but this is not included here. And of course, we have the execution physically isolated. We have the execution physically isolated from the host. So if the host is compromised, then the protection is still there. There's no chance for the hacker to get in that. And all what we do here is complementary to any other security measure. So if you have, for example, AutoSAR MACsec or other means implemented, then this is, let's say, in that sense, transparent or does not collide in any way. Yeah, finally, my last word is we have implemented this, so we have engineering samples available. We also have a small demo available here downstairs. So if you want to see how this works, then you come to our, let's say, non-existing unofficial booth and have a look to my small demo. And yeah, with this, I'm finished, and I'm happy to receive your questions.
Thank you very much for this insight in this, some secrets from NXP. And I have a question for sure, but first I would like to ask the audience, are there any questions?
Oh, yes, please.
Okay.
I also have a lot of questions, but I'll just, for now, keep it to one. You said that on a transmit filter, you are monitoring the CAN ID, of course, and then decide if you want to forward this message or use it on the CAN bus. So there's a delay, right? You have to first check if the, or do you?
There's no delay. The message goes out on the bus. It's completely there. So I can even decide after having received the CSC whether I have received the message correctly. And then still I have the end of frame field to issue an active error flag to invalidate the message for all the other transceivers or receivers in that sense.
Okay, thank you.
So do I understand it right that the transceiver only looks at the identifier? There's no option to have, for example, multiple senders of zero-length CAN messages, so where it's actually possible to have multiple transceivers for this, multiple transmissions of the same message from different nodes.
Yeah, so the transceiver is only looking on the identifier. Mm-hmm. And of course, depending on the configuration, you can also allow different nodes to send the same identifier.
Oh, okay.
That definitely would be possible,
that is
because
possible.
You can, of course, configure the transmission whitelist in each and every transceiver individually. Mm-hmm. And then, of course, if you assign a certain identifier to more than one node, then, of course, more than one node can send the same identifier.
Okay, thanks.
Yes, Florian Hartwig from Bosch. The whitelist needs to be stored inside the transceiver, But how do you get the data of the whitelist into the transceiver, and cannot the hacker use the same interface?
Yeah, so the interface we are using for programming is simply the CAN bus lines. Yeah? And as said, we assume that the configuration is done at the tier 1, so we consider the tier 1 production environment as secure in that sense. And when the configuration is done and tested okay, then the configuration is locked once and forever. So we are, let's say, burning a fuse, and then it's not changeable anymore. This is kind of inflexible, you can say so, but it's very secure.
My question, it's actually the question but already raised by Holger in his preface of the proceedings here. What is the end of the story regarding the transceiver? Will it later on become a standalone networking device just connected to the host by a generic interface, and everything is managed in this kind of transceiver device, or it's actually transceiver combined with a full protocol controller? Or what do you believe, or what is the strategy of NXP in this regard?
I don't think I can talk about the strategy, yeah, okay. But I can tell you what my belief is.
But I can ask.
Yeah, for sure. Yeah, one thing you see here is that we, let's say, have a CAN decoder, which is in that sense a fixed state machine in a set of simple policies that we can supervise. And as I said, we are thinking about concepts where we have a programmable core in the transceiver. So that would mean, of course, still the CAN-FD decoder to read the traffic and then the programmable core to react on it. So if, let's say, we need to do more than just investigating what's happening on the identifier, for example, if you think what Mr. Schreiner told us today, that they are putting the IPDUs in the CAN-FD frame, then likely one module only has one single CAN identifier, and everything is handled within the frame. So then I likely need such programmable core to look into the frame and then decide whether I need to kill it. Okay. And of course, what we also see is that in many cases there are very specialized signal processors, digital signal processors in modules, and those have likely, let's say, an Ethernet interface because they produce a lot of data, but still they have a need to interface with CAN. But they don't have a CAN peripheral. Yeah. And then we need to do something like SPI to CAN-FD or MII to whatever interface. So there might be some things coming up, let's say, where the transceiver needs to be more intelligent than today.
Okay. There are any questions more from the audience? Florian?
Second question. You know the purpose of the CAN fault confinement with error counters, error passive and bus off is to silence faulty nodes so that they do not disturb the communication of other nodes. Will your CAN transceivers with a whitelist also have some kind of limits to the number of error frames that they can send? Or will they be able to disturb the whole communication if there is one fault in the transceiver?
So for the whitelisting, it would mean, let's say, that if we have seen one identifier which is not allowed, then we only have one error frame on the bus, and then we exclude the node from communication. That's one thing. So there you're likely on the safe side. While, of course, if you do the spoofing protection in the receive path, then we would send, let's say, an unlimited number of error flags to invalidate all the messages that I do not want to see on the bus.
Okay. Then thank you very much.
Yeah, thank you.